All right. Good evening, everyone. Yeah, okay. So I know this is module 6, but we're actually going to take a look at module 5 tonight. I know we're skipping module 4 here. Let me just do this. That is module 5, because from the old syllabus 3 and 4 has been combined, and module 4 and 5 for this new syllabus, or what modules 5 and 6 were in the old. Now, there is quite a few new things in these two chapters that I don't have in the slides, especially for module 4. So I need to actually go revise the slides. So we're actually at a point now. Quite interesting that I think the module just after this one, slides and chapter, or rather the info in the slides and such match, but I don't want to go there just yet. And also for, what is it? I think, but the next chapter, I think you guys can do a self-study. It's actually not really that wildly difficult. It's just a lot of reading. Actually, with all the modules from 4 to, so 4, 5, and 6, they're all pretty much just reading. Then module 7, again, we're going to do power control, or things like SCRs, SCR circuits and chopper circuits, so we can take a look at that. And then I think, the second to last chapter will be PLCs, and then the last chapter will be robotics. Now I'm going to try for us to do, the thing is, even chapters 8 and 9 are very, I checked now, very dense chapters. They're not really, how can I say, we can't really go through them, quickly. But I'm going to try tonight with module 5 here, that's incorrectly named module 6. So I'll revise my slides, so we can go through this. But you guys will definitely have to do 1 or 2 of the modules as self-study. All right. Okay, so I'm going to quickly go through this. So though the subheadings in the new chapters are actually exactly the same: industrial safety devices and intrinsic safety. So so for industrial safety devices, we're pretty much going to take a look at photoelectric safety devices. Now, the textbook has an additional one here. Let me just quickly get my tablet here. It's going to make things a wee bit easier. So there is a second type of safety device that we're going to take a look at here. Yes, I can't remember what it's called, but it works on the basis of ionization and radiation. So if you guys go to chapter 4 again and look at radiation or radioactivity, there's actually quite a bit of information on that as well. Photo-optic safety devices, yes. Ionization, yes. So ionization, smoke detection, so it's just for smoke. There are 2 smoke detector examples in the textbook, one being photoelectric and the other being radiation based. So here we go. So you got, again, get a photoelectric one, and the other one works on the basis of ionization. Not 2 I's, only 1. Ionization. Right. And then flame failure protection, there's actually quite a few there. I actually only have one example in the slides, but I'll take you guys to the textbook just to walk you guys through some of the other examples. And then we also have positive and negative protection. And then for this second chapter with intrinsic safety, there's actually still quite a lot of overlap with the slides, so not too worried there. Right, so I'm just going to make sure about something here. So the purpose, let's see if the textbook actually, yes, textbook actually still has this information in it. So the purpose of electronic safety devices, there are basically 2 things that it does. First being that it will prevent injury or death of workers. Now, so injury or death in the workplace can actually be quite detrimental to productivity. And actually, it's also a very big financial hit that a business can take. So it is actually very important then that your safety devices will prevent inadvertent operation of your machines, um, especially in the case when an operator will be injured by that inadvertent operation. So inadvertent operation would be, if the machine is, for instance, if you take let's say a miter saw, for instance, if the shield is not in place on the miter saw, that saw shouldn't be able to operate, right? So it's basically using a piece of machinery for a purpose that it was not designed or intended for, right? So that's what you wanna avoid. Then, secondly, you want to prevent damage to your machinery. Um, so because again, machinery is quite expensive, so you don't want to have it damaged. And yeah, so your safety device will pretty much will prevent things like unskilled operation or unsafe conditions from being introduced um, into the workplace through unskilled operation. All right, so so there are two factors that we need to consider when we install safety devices. First, it must be fail-safe. So what that means is that if, let's say, the safety device itself is faulty, then operation of your equipment shouldn't be possible at all. Right, so if the safety devices, yeah, so it's basically, yeah, actually, I'm gonna kind of jump the gun here, and the operator should also not be able to bypass the safety device. So there also needs to be some way to prevent bypass. In essence, if somebody does bypass the safety device, that the safety device will still prevent the machine from being operated then in that case. Okay. Okay, then we have photoelectric safety devices. Now, yeah, so basically, what if, so this basically refers to electronic circuits making use of at least, or rather making use of optical means to get their feedback. Um, so whether that be one or two paths or multiple paths of feedback, but at least one path has feedback by optical means. So this can be a light ray, laser, um, even I would even throw infrared into this category as well. I'm just going to quickly take a peek here at the textbook that I'm on the right track here. In fact, before we go on to this, yeah, I just also want to show you guys something as well. But okay, let's just finish up this slide. So the optical relay, or rather what we usually do with we usually build what we call an optical relay. So it makes use of some form of light variation to get an electrical signal. So that's usually done through a photoelectric transducer. So we've already looked at transducers on what they are. Now, an optical relay will have a transmitter, so that will be a source of light. And then secondly, you will need a medium for that source of light to be transmitted or to be taken from one point to another. Now, generally, this is done using fiber optics. Can also be done via prisms, mirrors. So yeah, so there are quite a few methods that you can use to get light from one place to another. And then, of course, you're also going to need an optical receiver. And there, my tablet. Why is this thing not doing this? And then you have an optical receiver. Now that would be usually in the form of some photoelectric transducer, such as a phototransistor or a photodiode or a photoconductor. Also, you can call a light-dependent resistor or LDR, or any type of photosensitive junction devices, right? So anything that this will also include something like a solar cell as well in this case. Right. Okay, so before we get to a practical application, I just want to quickly jump to the textbook here. So the textbook actually, yeah, okay. 3 times went by that page. Every time when I share the screen, but in any case. Right, so So there are quite a list here of different types of not photoelectric, but electronic safety devices. So some of the most common ones, so you guys should know about circuit breakers. So circuit breakers is just to stop irregular incoming electrical current. Um, Actually, mostly to limit electrical current um, to a certain, I want to say a hard level, so that you don't exceed ratings for a downstream load, for instance, like a motor or something like that. Yeah, so it's basically to protect equipment. Then fuse. So fuses, simple metal strip or wire that basically, um, yeah, so it's basically a sacrificial component. So if there's too much current passing through a fuse, the fuse will burn, and that again will protect your downstream equipment. Ground fault circuit interrupters or GFCIs. Um, so yeah, so something that is a bit of an example for GFCI would be something like an earth leakage unit. Um, so yeah, so GFCIs will disconnect a circuit when the current between your neutral and live becomes unbalanced. And an example of where your well, a situation where your live and neutral will become unbalanced in a circuit is basically when you have either live or neutral touching ground, right? So you basically have current flow uh, somewhere else that is not within your circuit. It's actually how earth leakage unit also works. I don't know if you guys ever noticed the earth leakage unit, though the name says earth leakage unit, but you never connect the earth to your short ELU. You never connect your earth to it. Now that's because it doesn't need the earth. It just checks basically. There's some circuitry in there that basically checks that the neutral and live current is balanced, and if there is for some reason some imbalance between the two, the breaker basically breaks the circuit, right, or trips the circuit, right. So then you also have protective relays. So we're actually going to take a look at an example. So protective relays are usually relays with some circuitry, usually paired with so relays paired with transducers to provide some form of protection, whether that be protecting an electrical circuit or a mechanical piece of machinery, or you as operator on the machinery. So yeah, so that's pretty much what a protective relay does. So we'll take actually a lot of the examples that we're going to take a look at is kind of falls into this category. Surge protector, yeah, so this is pretty much to protect electrical and sensitive electronics from voltage surges from the electrical grid. Now, typically voltage surges can happen because of switching on the line. So maybe further upstream, ESCOM decides to switch in a new transformer into the grid. That can also cause a voltage spike. Lightning, that can also cause a surge on the lines of, let's say, a power pole such as struck by lightning. So yeah, so there's that. And then there's things like other devices that we can also take a look at. So so there's so we can also have devices that can prevent or detect operator contact with point of operation, and also to potentially stop hazardous machine motion if any part of an operator's body is within the uh, dangerous parts of the machine. Now, this can be things like, so you can use machine guards, so it can be fixed, interlocking guards, adjustable guards, self-adjusting. You can also get guards that are, I want to almost say, automatic. So when the machine goes into operation, the guard is then activated. Machine goes out of operation, guard deactivates itself. Um, and then, so actually already spoke about these 2 points. So I'm not going to mention them again. And then there's also then safety devices that are difficult for operators to bypass. So things like locking guards, safety connections, Optical relays. Now, we actually already spoke about this. We're actually going to take a look at some examples in a second, and we'll get to proximity switches in a second. It's actually interesting that magnetic is now a third option here. It used to be just inductive and capacitive, because magnetic is technically still inductive. But an inductive proximity sensor is usually the change in current that you measure, while magnetic proximity sensor is actually just purely just magnetism. But it's still going to use induction though. So I don't know. Those two are actually very similar. Anyways, yeah, then you have also, yeah, then we jump because we scroll a little bit and we're sharing the screen. Let me just do this, because it does seem like if I share my entire screen that it doesn't do that. Okay, but I would urge you guys to go read through this. So I'm not going to go through everything. There's also ultrasonic sensors, photo optic safety devices. We're actually going to take a look at an example of where a photosensitive or photoelectric device can be used in hydraulic press protection. Actually more to protect the operator in this case instead of the circuit. But yeah, the circuit that I have is a little bit more specific with the light sensitive device used here. But nonetheless, it's going to be the same thing. So let's quickly take a look here at what we have. Right, so in this situation, your light sensitive device, maybe pick color here. Your light sensitive device is going to be a light activated SCR. Now, basically what we have here is we have a circuit here that is powering a light. So that light source can be something like a laser, for instance. I think a laser would probably be the best thing to use here because it's very directional. And yeah, so essentially what you have here, so you have a transformer, you have a relay coil here. Now, under normal circumstances, so where the LASCR is getting struck by light, this is essentially then going to activate, so going to allow current flow through the LASCR. Right, so under normal circumstances, this is what you're going to have. That's then going to enable your press. So that switch is then going to be in that position there. And you as operator can then press on this foot pedal here, do your punching and pressing, no issues. Now, let's say for some reason you have a very, you have a work colleague that thinks they're very funny. They either bump you into the machine or they, for some reason, shove their hand in there. Just see if I can draw a little hand here. So somebody shoves their hand in there. So now what it actually does, that now stops this light beam from reaching the LASCR. Now basically what that's going to do is that's going to basically break this circuit here. And now you don't have any current flowing through your relay. And your press enable contact is then under spring pressure, then going to fall back to ground. So now, no matter how many times you step on that foot control, the machine is not going to operate. Right, cool. Okay, so that is pretty much how that setup is going to work. You guys also need to know the circuit as well. It has been asked a few times in exams before. As I can see with the new syllabus, you guys don't have to do the LASCR part. You can replace that whole circuit with just saying a light sensitive component or light sensitive piece of electronics. You can essentially achieve the same result with something like a light sensitive diode. And if you were to use a light sensitive diode, this part of the circuit is not even needed anymore, because that is essentially just to keep the LASCR going in this case, to keep the gate triggered there. I want to see in the textbook what they have there. Actually, the textbook has the exact same circuit setup. Actually, quite interesting, but yeah. Okay, and then we get to the smoke detector. Now, the smoke detector, you have a photoelectric method of detecting smoke, and you also have a by means of ionization also to detect smoke, so making use of radioactivity. So if we take a look at the photoelectric version of this, of a smoke detector, so essentially what you have is you have your transmitter and you have two prisms. Now these two prisms will then direct light through two viewing ports. Now one viewing port is going to be considered your control or your reference. So your reference viewing, your reference light is there. And that will typically then be run in a sleeve or can either be even be fiber optic or optic fiber. So if that's if that is fiber optics, that will then lead the light towards a resistor here, and yeah, so light sensitive resistor that is then attached to a difference amplifier, and then same with the so yeah, so you have also an exposed beam. Now, the exposed beam will also be directed towards a light sensitive resistor with a difference amplifier. Now you guys will kind of see that these amplifiers are kind of almost looks like they're polar opposite to one another. Now essentially what is going to happen here is the difference in voltage between these amplifiers, when let's say there is no smoke, then essentially the resistance of A is equal to resistance of B, then your output voltage is going to be zero, because the difference in voltage between the amplifiers is going to be zero. So amplifier A is going to give you, let's say, plus 5 volts. Amplifier B is going to give you minus 5 volts. Cool. Then if let's say we have smoke now, so with smoke interrupting the exposed beam, now obviously in that situation, the resistance in B is not going to be equal to resistance in A. So obviously your output voltage is not going to be 0 volts, right? So you're then going to have a change in voltage that then can be used to actually trigger a fire alarm or smoke detection alarm. Right, so I'm just going to quickly share my screen. There's also another, the other method, the ionization method. So I'm going to quickly just show you guys that. It's actually, yeah, so that's actually the first one. So ionization smoke detector. So this actually makes use of, yeah, so you basically have a positive, what you call it, positive electrode, and you have a negative electrode. So typically your negative electrode will be part of your container. And yeah, so there also is a collector that then goes to your trigger circuit, and you have a radioactive source. Right, so basically, yeah, so this chamber is also open to the air, and yeah, so typically what happens here is if smoke enters this chamber, so yeah, so it's basically going to change the amount of, so it's going to basically interact with the the particles given off by the radioactive source, and that's going to cause an imbalance here between the positive and negative terminals, which is then going to be picked up by the collector. Right. Okay, so that's one. We already looked at the photoelectric one. So yeah, so they can, yeah, so for the photoelectric smoke detector, so you guys can see it can be infrared, visible light, or even ultraviolet light that it uses. So yeah, so but the light is then directed in some way or another from a transmitter to receiver. Right, so there's that drawing again. Again, your amplifier circuits, that would be your receiver. All right, cool. Okay, then we get to flame failure protection. Now, again, there the textbook does mention a few methods. The only method that does have a drawing with it is the what you call it, the hot electrode version of it. Just want to see what they call it in the textbook, because with the old syllabus, that was pretty much the only detector that we looked at. I just want to see here, flame failure protection mechanisms. This is interesting because they don't say what this one type this is. But this is more for industrial furnaces, but there are other detectors as well. So you have let me maybe quickly share the screen here with you guys. We can go on. So yeah, so for flame failure protection, you have ultraviolet. Yeah, so basically, they can actually detect the UV radiation that's given off by a fire. So you can actually measure that, basically measure it directly. Um, and yeah, so ultraviolet detectors will also react to electrical discharges such as lightning and also welding sparks as well. That also emits a lot of ultraviolet light. Infrared detectors, again, anything that generates heat is also gonna release infrared. There is a drawback with infrared detectors, is that they can give you a false alarm. As yeah, if you have any other hot gases or surfaces um, close by your fire or close by your burner, then that can also trigger a response. Uh, yeah, so then you can have the combination of the two. But yeah, but then you also get multi-spectrum infrared detectors, again, making use of infrared. Thing is, you can then kind of fine tune the thing to certain frequencies or certain spectra of infrared, and no, you can even, I believe with these, you can even, what it looks like, you can also do adjust the distance of detection as well. So you can actually have a sensor that can maybe just detect up to a certain distance, and then anything beyond that is not really registered. So you can actually then reduce your risk for false alarms. Now, the circuit that we're going to take a look at, which is this one, so I'm just going to quickly go back to the slides. So this actually makes use of, yeah, so I would say this is a hot electrode detector, I would describe it. So this makes use of a ring-shaped conductor that is made from a refractory metal, so a metal that can handle very high temperatures. So a typical metal that would be used in an application like this um, would be tungsten. Right. So that will then act as your positive electrode. So your burner will then be your negative electrode. And yeah, so if you guys take a look at a flame, for instance, a flame is a high impedance medium, which means you're going to have a really high voltage across that resistor R1 there. And yeah, so so you're going to have a really high voltage across that point, and your field effect transistor here is then going to be biased by that high impedance voltage divider that we have here, that is then grounded by the flame. And if the flame goes out, for instance, the bias on your UJT here is reduced, and that SCR is then triggered on. Right, so this SCR is then pulled. Actually, no, lying here. So you're going to get conduction through here. And that's then going to trigger that SCR, and that's then going to trigger the relay, which is then going to trigger your solenoid control. Right, so basically it's going to open up the fuel solenoid to the burner. Right, and that's in the event when the flame goes out. Because what you don't want is you don't want fuel pooling in your furnace, and then when the burner is ignited again, you basically going to get a massive explosion then in your furnace from fuel just hanging around there. Right, so that is pretty much what this circuit needs to prevent. Okay, and then a typical question in the exams though that I've seen before, and I'm pretty sure that will be done again, is so usually what is done is you guys either need to explain how this works, or a very common question on this circuit is they give you the circuit, but none of the components, none of the components are named. Then you guys have to go and name all the components. Right. So in some cases like R1 here, that's luckily a double double thing. So if you remember one, the other one is easy to remember. So yeah, so then it's just remembering the other components. But I mean, if they give you the circuit, it's not really, it shouldn't be too difficult. Right. All right, and then there's the concepts of negative and positive protection. Positive protection is applied whereby operation of your system can only be justified if all safety conditions are simultaneously fulfilled or all fulfilled at the same time. So, so that is then expressed by a logic and function, um, which basically means that your safety devices uh, for a particular machine will then be connected in series. So an example of that would be overcurrent protection of a motor. So overcurrent protection will always be in uh, series with the device that it's protecting. So yeah, so if that device is not present, then the machine can't work. Right. So if it's not present or operational, then machine cannot be operated. Negative protection, on the other hand, can be described with a logic or function. So basically, what that means is that with negative protection, you don't need all the safety devices doesn't need to be in place, and they're essentially connected in parallel. So an example of this would be your no voltage protection in the case of DC motors. Though I think this example is not too good an example because typically your no voltage protection on a DC motor usually operates a series connected device in turn. But I mean, if you bypass the no voltage protection, then well, you bypass the no voltage protection. But it's a little bit difficult to bypass this overcurrent protection without issues. Well, you can, but I mean, you're gonna burn your machine if you do that. Anyways, then we get to intrinsic safety. Now, intrinsic safety, so just gonna basically, so the textbook also actually goes into quite a bit of detail with this. So it has a lot to do, you guys will see it has a lot to do with ignitable environments. So things like fuel, um, believe it or not, things like, what do you call it, where you have a lot of particulate in the air. So things like powder. So that also counts as an ignitable environment. Um, so yeah, so what an intrinsically safe um, system um, is basically a system that is designed to prevent high energy sources, so either electrical, chemical, or a combination of the two, from placing ignition capable currents or voltages on wires leading to hazardous areas. Now, hazardous areas would be where you have your ignitable atmosphere. Uh, so basically what intrinsic safety does, it describes protection techniques for electrical wiring and equipment, as well as for flammable atmospheres. And yeah, so mainly what we're going to take a look at in this section is explosion protection techniques. And typically what this will involve is to prevent faults in lower power measurement and control systems from igniting flammable atmospheres in hazardous areas. So essentially, our goal here is to reduce the amount of energy supplied within a hazardous zone, or to contain that energy supplied in such a way that it's not exposed to the flammable atmosphere. Right. So essentially, the definition of intrinsic safety is that we want to reduce the energy available in a hazardous area to a level where sparks or uh, to such a level where it's too weak to produce ignition of the atmosphere. I think the textbook has a bit of a better definition of it. Yeah. So here's the actual definition. So yeah, so equipment and wiring is then incapable of releasing sufficient electrical energy or just energy in general under normal and abnormal conditions to cause ignition of any specific hazardous atmospheric mixture. Right, so abnormal conditions here, so you guys will see what I have in the slides is pretty limited, but I'm going to go to the textbook on this one. Textbook actually lists the abnormal conditions very nicely in a list format for us. So I am going to adjust the slides for that. And once I've adjusted the slides to the new format, I'll put it up again. I'll just put the ones up tonight for tonight as well. So yeah, so here we have a list of abnormal conditions. So it will include accidental damage to any part of the equipment or wiring, insulation, or other failure of your electrical components, over voltage, adjustment, and maintenance, or anything that is very similar to what's already listed here. Right, so I believe I have the rest in the slides. I usually kind of fly through this part. Okay, so yeah, so that's the 3 steps. Okay, so I don't have everything here. So there's also your energy levels. So again, zone 0, which is essentially where you have your, I would say your hazardous area. Then you have, so that's pretty much where your gas or air or your ignitable atmosphere is going to be continuously present. Zone 1 is where your gas air mixture will be have a very high likelihood to occur under normal operation. And then zone 2, where you have a less, yeah, so with the likelihood for your gas air mixture to occur in those areas to be very unlikely. Right, so there's also a picture then to describe what zones 0, 1, and 2 are. So this is kind of, you can kind of see that as your different types of hazardous area. So so yeah, so there is so the loop concept that we have here is that when evaluating equipment for intrinsic safety, all the elements of the complete loop must be considered. So basically everything from all the way to input to output and back. And an instrument can only be considered intrinsically safe if it has a self-contained low energy power source, so something like a small battery or solar cell that is isolated from all other power sources. Right, so we can also just actually want to quickly take a quick look here at the textbook as well. So yeah, so they also speak about the energy levels here. Okay, so I'm just going to quickly jump to the textbook, just show you guys here. So I'm going to actually need to update the slides quite a bit. Right, so there are some things to take into consideration. So there's your cost of equipment, cost of installation. Right, so it's pretty much still the same as what you would have for a normal installation. It's just you're working at much lower energy levels. Flexibility. Okay, so yeah, so there's that, and then also hotspots. So something also to consider. So yeah, so if you restrict the electrical energy available, yeah, so if you reduce the amount of electrical energy, that is also going to basically we get back to this whole thing of having the energy reduced to such a point that any sparks or hotspots that you can get will be won't have sufficient energy to ignite the atmosphere. So that's actually very important. Energy levels also need to be considered. So we kind of already looked at that. So the energy levels are pretty much going to be determined by your specific gas or your specific atmosphere, concentrations of gas, voltage and current levels, energy storage elements. So this is things like batteries and such. And also includes capacitors, by the way. Contact with your contact materials, so materials that your components are going to get into contact with. Contact size, so that's also your I believe that's things like, I don't think it's contactors, but in any case, just, oh yeah, so it is actually your contacts. Yeah, actually I see now. So your contactors have actually been a better term to use. But yeah, and the speed at which you can open and close the contacts of contactors and relays, right? Because the quicker those mechanisms can operate, the less chance of sparking occurring on your contacts. And that depends also, like if you have like a mechanical, like mechanically or magnetic relays, that's obviously going to be physical connections being made and unmade. But if you have things like transistors, for instance, so transistors, you basically just going to have electronic operation. There's no moving component. Okay, so yeah, so there is the definition of a hazardous area. So it's any location where you have risk of an explosion, and yeah, obviously every hazardous area is going to be different, depending again on this list of um, things given to us. There's the zones. We already looked at the loop concept. We are going to take a look at the 3 basic steps now. We'll do that. I want to see methods of construction. So we actually already looked at a lot of this already, so I'm not going to, and some of the stuff are coming up in the slides in any case. Right, so 3 steps in determining intrinsic safety. You do circuit analysis. So essentially what you're going to do is you're going to design for or do analysis for the worst possible conditions. And then you will then consider all possible modes of failure for each component and what its effect will be on the energy levels within your hazardous areas. Evaluation. So you're going to try and assure a reasonable margin of safety under your worst possible conditions. So you guys will see this phrase is actually quite important, because if your circuitry operates correctly under the worst possible conditions, then your circuitry is going to be more than sufficient for any other conditions. Construction review. So again, to ensure that your critical components are reliable, um, that your newly designed circuit will function as planned. Right, so also very important, if your critical components, so if there's a component on which everything or the correct operation of your intrinsically safe device depends on, better make sure that that component is sufficient and reliable enough for your intended purposes. I just want to see here with the intrinsically safe transformer construction. Actually, it is still in the textbook. It's just the order of it's a little bit different. Okay. Right. So essentially, yeah. So it's actually, yeah. Okay. So it's actually for transformer construction. Yeah. So transformers can be constructed so that they can be presumed not to be fail unsafe. Right. So typically what is done with transformers, you can put gas. They're usually used with heavy grounded shields between the primary and secondary windings or some form of equivalent construction. And yeah, and so in a lot of cases, I think in South Africa this is particularly the case. Transformers must be able to pass a 1-minute insulation test at 1,000 volts plus twice the rated voltage after a burnout test. Now, what the burnout test involves is that the secondary windings are short-circuited. So if you guys just think about if you think about a transformer, let's say step-down transformer, obviously you're now going to have a lot of current flowing through the secondary side and a very little current on the primary side. Now, the primary side windings is then put at rated voltage for 6 hours or until the transformer burns out. And yeah, so if the transformer burns out, then okay, it burns out, then transformer dead. But if it doesn't burn out, then it needs to be able to pass this 1-minute insulation test. Right. And then you get isolation by encapsulation. So typically what is done here is, this is typically done for capacitors or very big capacitors. And yeah, so the capacitor is essentially then treated like a battery in this case, of equivalent voltage and, well, not really capacity. Capacitors have very low capacity compared to a battery. And then essentially what's then happening here is that we can make the circuit safe by installing a resistor in series with the capacitor to limit the current to a safe specified value. So this is particularly the case if that capacitor is discharging, right? So that doesn't just dump all its charge in one go and cause basically a current spike and potentially have a spark forming and having in that case then have enough energy to ignite the atmosphere that the circuit is operating in. And so essentially the capacitor and resistor is sometimes encapsulated together. Usually what this means is that the capacitor and resistor is essentially kind of they're cast in resin to essentially prevent that junction between the capacitor and resistor from coming into contact with any other portion of the circuit or exposing it to any so exposing it to any conductors that could potentially cause sparks and hot spots and whatnot. So so that's then encapsulated and basically kept from getting into contact with the hazardous area. And then we also have current limiting resistors. So essentially, if you have equipment operating inside a hazardous area, so we need to limit the current through those devices. So you can have current limiting resistors for that. And you guys will note as well, a lot of these devices that we're going to take a look at has a lot of redundancy built into them. So instead of just one resistor, we have two. So this is then if, let's say, for some reason this resistor fuses or somehow short circuits, then the other resistors there still to limit the current. Then there's also so we're actually looking at shunt protector. So this is series protective devices, shunt protective devices. So shunt protective devices, something that is most commonly used in this role are diodes, specifically things like flyback diodes. Now this is actually very helpful for just protecting circuits in general, and not necessarily just to make a circuit intrinsically safe. So essentially what can happen is, if we take a look, this can even be the coil, not just of a transformer, but also of a relay. Right, so if that relay coil is de-energized, so remember, you now had a magnetic field on that coil. Now with the magnetic field collapsing, that's then going to try and continue push current to try, so it's basically going to continue to push current in the same direction that it had been flowing originally. And you're also going to have your voltage across your inductor change as well. Now, if you put a diode then in parallel to your inductor, that's then now going to provide a current path for the flyback, what we call flyback current, go back to the inductor. So essentially what you're doing is here, the inductor is then going to dissipate that energy through the diode and itself. Remember, this thing has a little bit of parasitic resistance to it as well. Right, so instead of that going back to your circuit and potentially destroying a transistor or causing a spark somewhere, it is contained at the coil itself. Right, now something that is to be considered here is that if that diode fails, that's then a problem. So you kind of have to make sure that that you have redundancy. So typically what is done is you can have more diodes put in parallel here. So maybe you want to put 2 or 3 diodes instead of just one, so that if one of the diodes fail, that the circuit can still operate. Right, so basically you want robustness, so that if there's also you want the thing designed in such a way as well that a single problem in your circuit is not going to kill all your diodes all at once as well. So that's also something to consider. So that's why this is there, is essentially just to limit the current. All right, and then we have the rating barrier that kind of combines the best of both worlds for series and shunt protection. So you have current limiting resistors, in this case 3 of them, and then you also have Zener diodes. So actually forgot to mention, usually it's a Zener diode. In the case of intrinsic safe devices, because the xenodiode will clamp the voltage to a fixed level. So in this case here, we have the xenodiodes clamping the voltage to 30 volts. And yeah, so you have basically your safe area on this side of your reading barrier, and out on your outgoing terminals, you have your hazardous area. Right, so basically this barrier circuit is placed just before, um, just before the wiring basically goes to your equipment in your hazardous area. Yeah, and then also something to consider there as well. So if that barrier is designed to limit against full main supply power, then equipment in the non-hazardous area, so in the safe area, can then be implemented without any regard to safety in the field circuits. And your field circuits would be the circuits within your hazardous area. Right, and then there are some conditions though that does have to be met. Your field devices connected to this barrier needs to be approved for use with a rating or xenon barrier. And yeah, so barrier protection is a little bit costly though. As you guys can see, it uses more components, but it does give you a bit more flexibility in terms of equipment that you can place within your hazardous area. All right, guys, then, well, actually on the input side, sorry. So on the input side of your barrier, so on the safe area, so you can, so you can do stuff on this side without too much worry that it will affect anything downstream. All right, cool. Any questions? That's pretty much where the textbook also stops. So as you guys can see, this is not really there's not really any calculations here. It's pretty much, read through the stuff, understand, and you guys also just need to be able to explain some of the concepts here as well. Right. Cool. Okay, guys, if there are no further questions, you guys must have a good evening, and I'll see you guys next week. Cheers.